In our last programming video, we wrote our program on a sheet of graph paper and hand-assembled it into a list of hexadecimal numbers, which we then meticulously entered into the Hero Junior using the bootloader program from its read-only memory. Well, in this video, we will still be writing our programs out on paper and hand-assembling them, but we can improve things in the data entry realm. The Hero Junior has a second way to enter machine language programs, but it involves adding a keyboard and screen to the robot. How do we do that? With the serial port we repaired in the last video. We use it to connect another computer to the robot as a terminal. To start off, we need a computer with an RS-232 port, perhaps something period appropriate to start with. Why not be cool, right? Here's a TRS-80 Model 100 from 1983. Should be just about right. It has a 25-pin RS-232 port, just like the one on the Hero Junior. In fact, all we'll need is a straight-through RS-232 cable. The internet provides. For the two computers to communicate, we need to match the RS-232 settings between both machines. Recall in the last video, we set the Junior's CPU board to 9600 baud. That means it will send and receive 9600 bits per second over its RS-232 port. I also happen to know it uses 7 bits per character and 1 stop bit and ignores parity checking. Let's take a look at the Model 100 and see if we can match those settings. The Model 100 boots into its main menu, and as you can see, it's also stuck in the 1920s. No ROM fix for this one so far, although I bet there's one out there somewhere. We use these 4 arrow keys to navigate to the program we want to run. In this case, we want Telcom, which is the built-in telecommunications program. 2 arrows right and enter. In Telcom, the first line on the 8-line by 40-column LCD screen tells us its current RS-232 settings. Let's look at them one by one. The first tells us the baud rate. Next are bits per character. Next is parity. Next is stop bits. And the last one is flow control. We use the stat command to change the settings. For the Hero Junior, we'll need 87I1D. So 9600 baud, 7 bits per character, ignore parity, 1 stop bit. And D? Now we need to run the terminal emulation program inside of the Telcom program. For this we use the function keys, matching the keys to the on-screen menu on the last line of the display. Term is above the number 4, so we select F4 to run it. And now we can turn our attention to the Hero Junior and use everyone's favorite.
Robot wizard. F, B, F, A. Press Enter to confirm, or C to change. Enter.
And we're rewarded with the D prompt. So, before we dig in, a quick explanation of what a machine language monitor is. Basically, it's a very simple interactive program that lets us look at the machine's memory, enter new data into that memory, check and set the microprocessor's various registers, and run programs. The monitor in the Hero Junior seems to be based on the one in the Heathkit ET3400 microprocessor trainer. The main difference is that with that machine, we use the keypad and display on the trainer, while with the Junior, we're using the keyboard and display of the terminal instead. So we'll be typing commands on the TRS-80 100 and seeing results on its screen. So let's start with viewing memory. In the last video, we added an 8K RAM chip to this robot, so we now have 10K of memory, from 0000 to 27FF. Since an unexpanded Hero Junior has only 2K of RAM, we'll assume that the first 2K of our memory is being used by the robot's operating system. So let's use the rest of RAM, starting at address 0800. To view memory, we use the M command. Notice we didn't need to type the leading 0 of 0800. The monitor is smart enough to add it for us. Apparently, this was an innovative feature in 1985. So the display tells us that location 0800 contains the hex value FF. Let's hit the Enter key. The monitor displays the next address in memory and its value. Apparently FF is a very popular value for a newly awakened static RAM chip. We can keep hitting Enter to view successive memory addresses. Give it a try. Yep, lots of FFs. To change memory, we can simply enter a hex value followed by the enter key instead of just hitting enter. So far so good. We exit M mode by hitting Shift 1 to enter an exclamation point character. At this point, we've exceeded the abilities of the bootloader program we used back in episode 4 when entering the Hello World program. It didn't let us see the current values of each location, only change them. In fact, let's go ahead and re-enter the Hello World program. 1, to get to know the M command in practice, and 2, to relocate it into our newly expanded memory. Here's a listing I've written out already. Notice that the only thing that has changed here is the starting address of the program. Instead of 05D6, we're now starting at 0810. Savvy viewers will notice I'm not starting the program at 0800, the start of our usable memory. There's a reason for that, but you're reading ahead. It will make sense by the end of the video. For now, just know that we're saving space for something we'll need later. There was one change I had to make to the hex data of the original Hello World program, the address in memory of the actual Hello World phrase. It's now at 081A, so the second and third bytes of the program have changed. Let's enter the entire thing using the monitor. To start, we type M 0810, enter. And we enter each byte one at a time, much as we did before using the bootloader program and the robot's keypad. Here we can see what we're typing, however. After the last byte, FF, we exit M mode with Shift 1, the exclamation point command. Now let's exit the monitor and run the program using the Robot Wizard from the robot's main menu. To exit the monitor, we just hit Reset.
Ready. Robot Wizard. 0810. Press Enter to confirm, or C to change. Enter. Hello World. Ready. Robot Wizard.
So far so good. Let's re-enter the RS-232 monitor.
Press Enter to confirm, or C to change. Enter.
If entering data into memory was all the monitor did, it would already be worth its weight in gold. But of course it does more. Let's try the I command. I stands for instructions, and it disassembles memory back into machine language mnemonics. We'll run it on the program we just entered. I works just like the M command, except it shows us the disassembled mnemonic instructions at each location, and it moves 1, 2, or 3 bytes at a time through memory, depending on how many bytes each instruction takes up. Continue hitting Enter to see each successive line of our program. Notice that everything matches our handwritten versions, except that the monitor does not add $signs to the hexadecimal numbers. Everything it displays is in hex, so there's no need. Notice also that things go off the rails at memory location 081A. What is ABA, and who put it there? What's happening here is that we've moved past the end of our program into the Hello World phrase at 081A. The first byte of phrase data is 1B, which just happens to also be the opcode for the ABA machine language instruction. The monitor's I command doesn't know the difference between machine language instructions and phrase data, or any other kind of data, so it just does what we told it and disassembles the bytes it finds at each address. It's up to us as the programmers to remember which parts of memory are programs and which parts are data. Hit Shift 1 to exit the I command. So we've seen how to enter, examine, change, and disassemble programs and data in memory. But we can also run programs directly from the monitor as well. The G or Go command transfers control from the monitor to another machine language routine. We can use it to run the Hello World program without exiting back to the Hero Junior's main menu. But since I know we'll run into some unusual behavior with the Hello World program, let's try the G command first with something simpler. How about a short routine that literally does nothing, then returns back to whoever called it? Here's just such a program written out. The 6808 actually has an instruction called NOP, or NOP, which stands for No Operation. All it does is take up a small amount of processor time and occupy a single byte of program memory. It's often used to set aside a bit of time or a bit of memory or both. For us, it's just an instruction to represent the other, more interesting instructions another, more interesting subroutine might have before getting to their return instruction, the RTS, at the end. Let's enter these 2 bytes into memory at 0800. And no, this is not why we left space there at the beginning. We'll get to that soon. Now let's run this routine from inside the program monitor and see how it goes. Unlike the commands we've used so far, we have to take an extra step to tell the G command where to go. Before using G, we need to preset the 6808's program counter. Recall from a previous video that the 6808 microprocessor has a number of internal registers it uses for its own purposes. We can look at all of these registers at once with the R command. Press R to see a list of the microprocessor's internal registers. The P register is the program counter, which tells the CPU where it will get its next instruction from. To view or set just the program counter, we select Control P. Like the M command, we see the current value. And like M, we can change the value by typing a new value and hitting Enter. Let's change the program counter to 0800. The starting address of our do nothing and return routine. Now with the program counter set, we can use G to jump to the subroutine. Unlike the other monitor commands, G is activated by typing 2 periods after the command. And it does not go as expected. Presumably, we jumped to the subroutine and executed the NOP instruction, but we most definitely did not return to the monitor. Press Reset to get control of the machine, and then Robot Wizard to FB F8 to get back to the monitor. So what exactly is happening here? The short answer is that the RS-232 monitor program is able to do what it does because it's driven by software interrupts. Because it needs to grab the state of the processor on the fly and start and stop program execution at will, it doesn't work like a normal machine language routine, and thus it doesn't quite know what to do when it encounters a regular old RTS instruction. So that explains what went wrong, but how do we fix it? Well, the monitor program has a method of forcing a return back to itself at any instruction we care to specify. It's called a breakpoint, and we can specify as many as we want when we issue the G command. What we really want to happen is for the do nothing routine to return to the monitor when it's about to execute the RTS command at 0801. So instead of the G command we used before, we type, and ta-da! We've run our do-nothing routine and returned to the monitor. The advantage of using a breakpoint is our routine will run as normal from the robot's main menu as well as from the monitor. The breakpoint does the work on the monitor side, and our routine operates as we expect it to, no matter where it's called from. So we're ready to try and run Hello World from the monitor. First, we'll set the program counter to 0810. Then we'll use the G command with the address of the RTS added in. And that's clearly wrong. This is why we started with the do-nothing routine in the first place, so you could see that the breakpoint should be working. So what's the deal? The save phrase command is also driven by an interrupt system, and it conflicts with the interrupts that drive the monitor program. So we need a way to eliminate the conflict. And the easiest way to do that is to do what the robot's operating system does when it has the same issue. It waits until the speech routine has finished speaking before doing something else. What we really want is a version of save phrase that says its phrase, but waits until it's done before it returns control to whoever called it. And here it is. This routine, which I call announce, is actually a wrapper that surrounds a call to the original save phrase with a loop that waits for the speech activity to stop at the end of the phrase. First, we call the save phrase routine just as we normally would in our main program. We're assuming that the calling routine has already loaded the phrase into the phrase address 1 variable in memory. Upon returning from this JSR, the phrase will still be in the process of being spoken. So we need a loop that waits for it to finish before we do our own RTS. The loop is here. First, we load the value from D841, which is part of the peripheral interface adapter that outputs values to the Votrax SC01 voice synthesizer chip. If that value is not 1, then the voice is still active. The BITA instruction compares the value in accumulator A to the number 1, and if they're not equal, then it loops back and loads the value again. Once D841 does equal 1, then the loop exits, and we return from announce with the RTS instruction. So let's enter announce into memory at 0800. Now we just need to change the call to save phrase into a call to announce. We'll change the address value 8000 to 0800. So we're literally changing just 1 byte in memory. And let's run Hello World again. First, we set the program counter. And then we enter the Go command with a breakpoint set for Hello World's RTS instruction.
Hello World.
And there we have it. We've mastered the basics of the Hero Junior's built-in RS-232 monitor. We'll be using it extensively in future videos. Next time, we'll explore the Hero Junior's other means of communication, those LED lights on its keypad interface. And we'll finally get to the bottom of all that seemingly random blinking. Come back next time as we expand our programming skill set and start to build a library of reusable routines. Join us next time as we continue our restoration of everyone's favorite 80s robot. And if you like this video, don't forget to
Like, subscribe, and ring the bell.